Hello everyone, my name is Kun Yang, and I'm pleased to present my research project on adapting foundation models to detect environmental and urbanization changes from remote sensing data. In this presentation, I will walk you through the motivation behind the project, the research questions, goals, the data and method I used, and also the results obtained so far. Let me start by explaining what change detection is. Change detection is basically the process of identifying differences in the state of something over time by comparing images taken at different times. As we can see, the black and white picture means the difference between image 1 and image 2. This is important in many areas, such as monitoring environmental changes or urban development and medical research. Now, according to an article called A Change Detection Reality Check, this article compared with other new models. The U-Net model has shown pretty good results for change detection task, which you can see in this chart. Because of this, I choose U-Net as the base model for my project. The U-Net model is a type of deep learning architecture originally designed for biomedical image segmentation. Known for its U-shaped design, it consists of contracting paths and expanding paths. Contracting paths, we can also call it encoder, is on the left side of the U. The contracting path follows the typical architecture of the convolutional neural network. It consists of rapid application of two 3x3 convolutional layers, each followed by ReLU activation function. This is followed by a 2x2 max pooling operation to downsample the image. As the image is downsampled, the number of the feature channels doubles, allowing the network to capture more complex features. At the bottom of the U, the bottlenecks layer connects the contracting and expanding paths. On the right side of the U is the expanding path. We also call it decoder. It performs upsampling through 2x2 transported convolutions, which halve the number of the feature channels, but double the spatial dimension. At each step, the upsampled features maps are connected with corresponding features maps from the contracting paths. This skip connection helps the model keep high resolution features that were lost during downsampling. Finally, a 1x1 convolution is applied to reduce the number of features channels to desired output, which is typical a binary or multi-class segmentation map. This structure allows the U-Net model to precisely segment the images by capturing both high-level and low-level features through its U-shaped design. Back to the topic, the main question is, how can we improve the base U-Net model to make it work even better? To do this, I'm testing a few ideas. First, adding attention mechanisms to help the model focus better on important areas. Second, using data augmentation to make training data more diverse and help the model generalize better. Third, trying different optimizers to find one that is work best. Finally, fine-tune the model's parameters to optimize its performance. For this project, I'm using two main datasets, Liver dataset and Wuhan dataset. Liver dataset is my primary dataset and is designed for change detection tasks. And the Wuhan dataset will be used later to validate the model on different datasets. Both of these are widely used, and from the figure we can see that a large number of papers use these two data every year. In terms of tools, I'm using Python and PyTorch framework, which is an open source deep learning framework. PyTorch usually used in computer vision, natural language processing, medical image analysis, time series analysis, and other fields. Here's how I'm conducting my research. First, building the base model. I started by setting up the basic unit model and running it on the leveled dataset. Second, use a hybrid loss function. To improve the model's performance, I used a combination of two loss functions, cross entropy loss, dice loss. This helped in balancing the importance of different classes and improving accuracy. Third, use data augmentation. Data augmentation involves creating variation of the training data, such as rotating, flipping, or altering the color of the images. This technique helps the model become more robust by exposing to a wider range of scenarios, which improves its ability to generalize a new unseen data. I will compare the model's performance with and without data augmentation by looking at the metrics like IOU scores, F-scores, precision, and recall. Fourth, adding attention mechanisms. Attention mechanisms are techniques that allows the model to focus on the most important parts of the input data. By highlighting relevant areas, attention mechanisms help the model make more accurate prediction, especially in complex tasks, like identifying little changes in images. The attention mechanisms in this model, I used the SE layer, squeeze and extension layer. It works by first squeezing global spatial information into a channel descriptor, then exciting the network by recalibrating the importance of each feature channel. This allows the model to adaptively highlight important channels and suppress the less useful ones, improving its focus on relevant features during change detection. Next, I choose two different optimizers, ADAM and SGD, to see which one gives better results, and at last, tuning the parameters to find the best one. So far, here is my result. First is data augmentation. After running 100 rounds, although the difference between these two is almost the same, but we can see in this figure, the IOU score curves grow more steadily when I use the data augmentation. So I will use the data augmentation in the following test, and considering the computer performance, I will only use 60 rounds in the subsequent test. This is the data comparison before and after attention mechanisms. Based on these attention mechanisms, I test two different optimizers. I found that using the data augmentation, adding attention mechanisms, and using ADAM optimizer get a higher IOU score. This combination helped improve the base unit model's performance. However, these results are not final. I'm still working on the further tuning the model to achieve even better results, and also run more rounds than the case in the test. Moving forward, I will run the model on the Wuhan dataset to validate the results and make sure it performs well on different types of data. And that's all. Thank you.